Welcome, everybody. Welcome to Organic Chemistry 2, Wednesday lecture. I hope you all got your emails from earlier today. Hopefully good news for all involved. And we're going to continue with our exploration of carbohydrates right now. So what we have over here is the cover page of test 4 for almost all of the most recent exams. Amino acids are on top. We will study those later. Bases used to make DNA and RNA, we'll be using those later as well. Fatty acids, we'll look at those when we study the lipids chapter. And the one we're currently focusing on, so we'll try to make it a little bigger, are D-monosaccharides. That's the ones we started using on Monday. We're going to be focusing a lot today on reactions of carbohydrates. So on our next page, we have a little information here. I know it's a little fuzzy. I took these from Moodle. These were more recent additions to Moodle, so they're a little cleaner. These are very old notes here. I believe these notes were made before a lot of you were born. But I think we can get the take-home message here. Here's a hemiacetal of this sugar. This is a new thing here. What does that little squiggly line mean? Well, it means it's a mixture of beta, that would be the OH cis to the CH2OH, and the other anomer, where the OH is sticking down and is trans to the CH2OH, so it would be alpha. This is a new form of isomer called anomers. Anomers are different only at the anomeric carbon. Which one's the anomeric carbon? The carbon that has 2 bonds to O. There are no other carbons in this sugar with 2 bonds to O. We can have anomeric acetal, hemiacetals, or acetals. That would be a carbon group over there, alpha being down and beta being up. Cis is beta, trans to the CH2OH is alpha. The important thing to know is that hemiacetals are always in equilibrium with their open form. This equilibrium shows that it's favored to be in the hemiacetal form. And what that means is a carbon with nothing but sp3 hybridization, sp3 and all sigma bonds is what I wanted to say is more stable than carbon with a pi bond. So hemis are favored over open forms. And we open this up and we see we have 2-deoxy-D-ribose. Any reaction we studied previously of aldehydes is now germane. So a reaction such as, hello, I thought I had the pen on. And here we go. Example. If we reacted that with, say, not PCC, I don't want to use chromic acid either. How about something that reacts only with aldehydes and doesn't touch alcohols? This chemical here is called Tollen's reagent. And it reacts to make carboxylates. And we've got R down here because none of this changed. And Tollen's reaction specific for aldehydes, and it oxidizes them to carboxylates. And my minus charge is a little bit off. It's a little far away. And with these notes over here, we see where the top carbon only is oxidized is called, if it's a carboxylic acid, it's called an aldonic acid. We have to know that. The conjugate base of an aldonic acid is not surprisingly, if you react that with KOH, you'll make an aldenate, which is the conjugate base of an aldonic acid. And that's what this is. It's an aldenate. Named so because it came from an aldehyde that got oxidized. All right. Now, if you had an acetal, that reaction is not going to happen because this is not in equilibrium with its open form. So how do you prevent monosaccharides from reacting? Well, you make them into acetals, either by mixing them with another sugar to make a disaccharide or some other carbon group. Down here, we have another example where I reduced the aldehyde. And then I made the aldehyde into an etol. That's a functional group. What is an etol? A reduced monosaccharide. I bet a lot of you have etols sitting in your pocket right now. Monosaccharide. Look at your sugar-free gum and you might see mannitol. That would be from mannose becoming an alcohol up here. Sorbitol is another common one. It's from sorbose. It's not on this handout, but sorbose can be reduced to an alcohol, and it's called sorbitol. And why do these things work as a sweetening agent in a sugar-free gum? It's kind of funny. You took a sugar and reduced it, and now you can say it's sugar-free. Isn't that funny? Well, it's because the bacteria recognize the aldehyde portion, which is no longer present, so the bacteria don't know what to do. All right, I think there's something on that on the next page. What else? There's a new reagent down here called Benedict's reagent. And it's very similar in what it does to Tollen's. Benedict's reagent. And it, like Tollen's, takes the aldehyde on top and makes it into a carboxylate. And I have a good question for you now. How can fructose cause Benedict's to turn red, which is the color after the reaction's over? You took a blue chemical. Benedict's chemical is blue. It's a buffered solution of copper 2+ ion, which in aqueous solution is always blue. And it made a precipitate that was red. And it turned red. When fructose does not have an aldehyde? Great question. Teacher's favorite. We have fructose right here. And left, right, right. Stolen straight from page 1. And I'm going to circle everything down here. And what happens is that sugar becomes this. I put that as a squiggle because it can be on the right or the left. And Cu2O. is produced as well. And this is going to be our old friend coming to play here. The chemicals in the buffer, either it's an enzymatic buffer or some other kind of aqueous buffer. Say we're using acetate buffer, where you have a base and its conjugate acid. What happens is this alpha hydrogen, yep, our old friend alpha hydrogen to a carbonyl, is in equilibrium with its, what do you call it when you do a tautomerization? What are the two molecules called? Answer, tautomers. So here's the tautomer, and it looks like this. Well, let's do it in blue. I'll put that in black so you know it's a new H. And then we have R down there. I didn't call it R. And you'll notice this is an enol in two directions. This is very common with carbohydrates. It's called an enediol because we made an enol that wasn't there before, and we already had an ol, and it's attached to the ene as well, which means you can do another tautomerization to make an aldehyde using the same combination of chemicals. And I need that arrow to be smaller, or yeah, smaller and moved. And you get an aldehyde. There's nothing new here. We've been doing tautomerizations for 2 semesters now. And this time it's an aldehyde, which we know full well can undergo the reaction. And you got an OH here and an H. Left-right mixture of both. You put the new H on, could be the left or the right side, doesn't matter. And we get the reaction we saw up here, where Benedict's Cu2 plus starts blue and becomes Cu1 plus when it's combined with oxygen as a red precipitate. That does not look like copper, does it? So we say that sugars that can do this, that can cause other chemicals to become reduced. Copper 2 plus went from 2 plus to 1 plus. That's a reduction, right? We say this is a reducing sugar. You may have heard that expression before. So what are reducing sugars? This page is getting kind of full. It's going to be real tiny if I add more stuff to the bottom. Reducing sugars, I'm saying it orally, are sugars that can cause other chemicals to become reduced, as their name implies. We just learned that hemiacetals, by themselves, they can't do the reduction, but they're in equilibrium with the open form, which can do the reduction. Now, if we had a hemiacetal of fructose, this is fructose, it's in equilibrium with its open form, which I drew right here. And it's in equilibrium. These are all equilibrium arrows, by the way. I didn't show them as that, but I should have. It's in equilibrium with an enediol that's in equilibrium with the reducing form of the sugar, which causes the reduction. And you know what Mr. Le Chatelier says about removing this molecule from this equilibrium by doing this reaction. That's not an equilibrium. That's a one-way ticket. I'm sorry. No backwards on that one. This guy's a precipitate. That means not coming back. And you're stuck here and you've got to replace this molecule. So it takes it out of this equilibrium, which means you got to replace this molecule, which means you take it out of this equilibrium. Everything ends up over here at the end, even though you started with a ketone that by itself cannot do the reaction. Isn't that fascinating? So what things are reducing sugars? Two things. Open forms of monosaccharides and hemiacetal forms of monosaccharides. Those are the two things that are reducing sugars. That's it. I'm not going to write it down. I'll say it again. The open form, which is like everything pictured on page 1. Everything pictured on page 1. Down here, those are all reducing sugars. Hemiacetals of any of these are also reducing sugars. Acetals of any of these are not reducing sugars. And who cares about reducing sugars? There's a very large percent of our population that cares about reducing sugars because they have to monitor how much glucose, free glucose, is in their blood. Glucose fits as a reducing sugar, and if that starts building up in their blood, then they need to metabolize it. And some people do not have the required levels of insulin to metabolize their reducing sugars, so they have to take their insulin shots when their reducing sugars get too high. I just want to point out everything on this page can be made into its conjugate base. And before we leave this page, and this will be our first break, we have to know that aldaric acids exist. We will not learn a chemical that can convert a normal monosaccharide to an aldaric acid. On the test, I will just say, draw me D-mannose and draw me its aldaric acid. And I expect you to make a carboxylic acid both on the top from the previous aldehyde and on the bottom from the previous primary alcohol. And an enzyme would catalyze that reaction. Yes, you have enzymes inside you that catalyze the formation of aldaric acids. And you need to know what a uronic acid is as well. A uronic acid doesn't touch the top position. It only oxidizes the bottom position to make a uronic acid. An enzyme would do that. And this one would make mannuronic acid. And kind of the conjugate base, careful how you say that one. You might need to go to the restroom if you don't say it right. Mannuronate. And that's all you need to know about oxidized monosaccharides and reactions of reducing sugars. Sometimes reducing sugars. If you do this reaction going from here to here, the sugar is actually becoming oxidized. That would be a reducing sugar. So we already talked about that. No need to mention it again. And I'll see you after the break. We will pick up over here. And we have to learn. This is a nice little summary page. I stole it straight from the notes at Moodle. Nothing here doesn't already exist at Moodle. And it's a nice little summary of reactions you're responsible for. And we'll pick up right here very shortly when I see you.